So it's a pleasure to have Dimitris Achlioptas giving a talk in the WNCG seminar. So Dimitris is in his PhD in Toronto, and he was a researcher at Microsoft Research for several years, and now he's a professor in UC Santa Cruz. He's working on randomness and computation. He has received many awards, including NSF Career, Sloan, and ERC Starting Award. And he'll tell us about codes, which is not his usual thing, and I guess stochastic integration. So,
thank you, Alex. Can you hear me in the back? All right. So this is joint work with my student, Paige Young. And the general idea is, this is a talk in which we took a theoretical idea and then added more theory to make it practical. So this is true. So here's what I'll talk about. The overall setting is that we have a large domain, so we have n variables, and these are finite variables. And we have a function f that is sitting on top of that domain. And we want to sum f over the entire domain, and sometimes I will call this integrate. And that's it. That's the problem we want to solve. Two key things is that the domains are finite and that f is non-negative. So when you compute this sum, there are not going to be any cancellations. And this is a rather ubiquitous problem. For example, in probabilistic inference, computing this sum amounts to computing the partition function of your graphical model. In hardware and software verification, you often want to compute this sum because it helps you generate test inputs. And in fact, I'll go as far as say that what I will talk about is sort of a generic alternative to using Monte Carlo sampling in a very large number of contexts that derives its power from the use of and continuous development of powerful optimization software. Hi. So clearly being able to compute this sum is a so-called Sharpie complete problem. It's worse than NP complete, so we're going to make a couple of compromises. The first one is we're going to be happy with approximations of the sum. And the second one is that our algorithm is going to be probabilistic, so there is going to be some probability of failure. Moreover, implicitly throughout the talk that I will assume that P is equal to NP, and I will explain the sense in which I mean this. So
you assume P is equal then?
Yes, yes. So I'll assume that P is equal to NP and use that assumption to try to do something harder. Okay? So I hope the setting is clear. And so for the rest of the talk, to simplify the notation, we're just going to assume that the domain is the binary cube. And I'm going to settle for a 32 approximation rather than an arbitrarily good approximation. And hold on a second. Oops, something got skipped here. There was a panel here that was supposed to say that my goal is to be able to get z within a multiplicative 1 plus minus epsilon with arbitrarily good probability, and we will be able to do this. Except for the purposes of the talk, we're just going to stick to omega being the cube and just get a 32 approximation. And it's easy to generalize to arbitrary accuracy and other finite domains. And observe that a 32 approximation is a very reasonable thing because typically z is exponentially large in n. So you have 1.3 to the n times 32. So here's the general idea of the talk, and that idea is not ours. In fact, most of the talk is going to be devoted to explaining an idea that has been developed by Selman and Ermon in the last 5 years, and that's sort of the theoretical idea that we're going to improve upon. And the general idea is this scheme. We're going to run this loop that says for I from 0 to n, where n is the number of variables, repeat theta of e to the minus square times, where eta is the accuracy that you care. And here's the meat part. Generate a random subset of the domain, and I'm not going to tell you yet how, of size roughly 2 to the n minus I. So this is going to be when I is 0, this is the entire domain. When I is n, this is just a single point, and everything in between in powers of 2. And having generated such a random subset of the domain, I will assume that you can solve this problem. You can find the maximum of f over this subset of the domain in a reasonable amount of time. In other words, I will be assuming, for example, that if this is a graphical mod, then you can solve the map problem relatively reasonably. Or for example, if it is a satisfiability problem, that you can actually find satisfying assignments if they exist in reasonable times. And while these are obviously NP-complete problems, in practice there is tremendous success in scaling to problems of huge size. In particular, performing this maximization is something that we will generally delegate to something like Cplex and exploit the fact that people spend, millions of dollars and thousands of humans' hours in actually developing code that can do this in practice.
So is RI uniform at random?
I haven't said anything about RI yet. The only thing I've said is its size. Okay.
And when you say the function, I mean, you'll get more specific, I guess, but
yes.
Should I think of a simple function? Or
good, sorry, good. Actually, I wouldn't have, and it's a great thing that you ask. Eventually, there will be times where we will think of f as completely black box, but the truth of the matter is that in many interesting domains, if you think of f in terms of a factor graph, f has the property that it can be written as the sum of many microfunctions, each of which binds a small number of variables. So for example, in graph coloring, you can think of f as something like e to the minus number of monochromatic edges, and then you have one microfunction per edge telling you that these two endpoints.
So you want to factorize it into...
I will not assume that,
okay.
But it is a good idea to keep in the back of our heads that if you were, that f typically does have a representation in terms of a sparse factor graph. I will not strictly speaking assume this, but then we will see how this comes into play. For now, f is just generic, okay? But perhaps another good mental model would be you can think of f as specifying some kind of a linear program and you want to count the number of integer points inside the program. Okay. Is there another question? And by and large, I'm not going to address this point further. I will assume that you live in a world in which realistically for your needs this is something that you can do. Observe that if you can't really do this, then having any hope of being able to compute z is, significantly diminished. And there are many worlds in which being able to do this is actually pretty realistic. So the contribution of this talk is this. The entire value that I will provide in top of existing work is the suggestion that this random set R sub I should form an error correcting code. Okay, and that when you do this, things get better. Is this clear?
And so it's going to be a subspace?
Eventually, yes, but let me get to that because it'll take another half an hour to get to that point. So first I want to explain why independently of this, this chance may have any chance, this scheme may have any chance of success.
And you would still need to repeat it theta 1 over epsilon squared.
That's right, but epsilon is the accuracy that you want. So that's a pretty reasonable, and the probability, and by the way, I mean, there's going to be, sorry, I like it, for some reason there's a missing panel. The probability of success is going to be something like e to the minus a parameter, and the amount of work is linear in that parameter. So the convergence in probability is very good, okay? And the convergence with respect to the multiplicative factor for z is 1 over epsilon squared. And then I have this factor of n, which is the number of variables in the problem. Okay. So the beginning of all this is the following thought experiment. Imagine that by some kind of magic, you could sort omega with respect to the f value. So this is the maximum of f over the domain. This is the second biggest value, third biggest value, and so on. So I take f and I sort it in a decreasing function, in a decreasing fashion here. And then I would like to know what is the value of f over these doubling powers of 2. So this is 1, 2, 4, 8, and so on, for an example with 6. So instead of having 2 to the n numbers, now I have n plus 1 numbers. And it's not hard to see that if I could actually get my hands on those n plus 1 numbers, I could get a 2 approximation of z. And the reason is I can define this quantity, which is, as you can see, is defined only in terms of the b numbers, and this one, which is the same except for a shift of an index. And it's easy to prove that the L quantity is a lower bound for the partition function, the U quantity is an upper bound for the partition function, and U is no more than 2L. And there is also sort of a cute proof by picture. I think the blue is F sorted. Remember I had 64 points. And I also know the value of f at these 7 points. My upper bound is the area under the green curve. My lower bound is the area under the red curve. And the interesting part is to show that those two are related by a factor of 2. And to do this, you do it by horizontal slices, observing that in each slice, the ratio is at most 1/2. Because in the worst case, it's 1/2 inside here, but you also have the benefit from this part. So this gives you a 2 approximation. If you wanted to get a 1 plus epsilon approximation, rather than having this be 2, 4, 8, 16, you would make it 1 plus epsilon squared, and so on and so forth. So this gives us the 2 approximation, assuming we can get our hands on those n plus 1 numbers. And moreover, as it turns out, you don't really need to get those numbers exactly. If you could give me an estimate for each of these ordinals, which is within, you know, c to the left and c to the right of those other ordinals, I would be getting such an approximation. And instantiating this with c equals 2 gives us the 32 approximation that I mentioned. So in order for us to win, it has to be the case that for each of the red dots, we can return an estimate of it, which is within 2 red dots to the right and 2 red dots to the left. And if we can do this, then we get a 2 approximation. Sorry, a 32 approximation. Is this clear? Are there any questions up to this point? So everything now has been reduced to this. Can you estimate each of those BIs in this fashion? So, was there a question?
Sorry, I lost how you got to 32. I'm sorry.
I didn't really work through it. There is this generic statement.
Okay.
So c equals 2 gives me a 5, 2 to the 5 gives me 32.
You just chose 5.
Pardon?
You just choose, you prefer to set c equals 5 for your...
C equals to 2.
Okay.
So setting c equals to 2 gives me a 32 approximation.
Okay, but is there anything magical there?
No. It's just the cleanest thing you can do to just get rid of it quickly, okay? So now that's our ball game. For every single one of the red dots, for example, for this red dot, we have to be able to come up with a number that is inside this interval. The interval being defined as 2 red dots to the right, 2 red dots to the left, and if we can do this, we win. Okay? Moreover, as you can imagine, it is enough in some sense that I have a random variable that falls inside this interval with reasonable probability. It doesn't have to be that it is deterministic. So thinking of these 2 endpoints as the upper and lower numbers in the next slide, there is this very generic lemma that says you have 2 numbers, the upper number and the lower number. You have a random variable which with probability at least 1/2 is less than the upper number, and with probability better than 1/2, sorry, when I'm at least I meant better than 1/2. It is at most the upper number, and with probability better than 1/2 is it at least the lower number. Well, then if you generate independent samples of that random variable, and importantly you take the median, not the mean, then the probability that it's going to be where you want it is exponentially large in your bias, and more importantly perhaps the number of samples. So linearly in the number of samples you can actually make this probability incredibly good. So now we have reduced the problem to saying for each I, give me a random variable which has the property that it is not too far away from BI with reasonable probability. And we're running 2 distinct risks. One is being too big, one is being too small, so overestimation and underestimation. And we want to have better than 1/2 chance that neither of the 2 things happens. And as it turns out, those 2 risks are not symmetric at all. The probability of overestimation is very small. And here's somehow an idea that it would be good if, excuse me, here's a picture that would be good to carry. So remember that we're trying to estimate B sub I, and we are okay if we are within 2 red dots, like to the left of this, and to the right of this point. Now, the way that we will do it is we are going for any particular I, determine a random set such that for every element of the domain, the probability that it is in the set is 2 to the minus I. And I don't mean independently here. This is just a marginal probability. The only thing I'm telling you is the expected size of the set, okay? And having done so, my estimator for B sub I is going to be the maximum of the function in that remaining random set. So for example, after I perform my randomization, there are 2 to the I numbers here. I expect 1 to be alive in here. So things go poorly for me if the one surviving element happens to be to the left of this line. And you can see, that's not going to be terribly likely to happen. I have good chances that it won't. Where by good, we will see that I just mean 3/4. And then the other thing that I want to happen is that after I form my random set, I expect 4 elements to survive from this region, and it better be that at least one of them survives, because otherwise I have underestimated. In other words, the bad event is that everything in here gets wiped out, whereas I expect 4 things. Okay, so these are my 2 bad events. One bad event is I have something surviving in here. That is overestimation. The other bad event is I have nothing surviving in here, and that causes underestimation. Is this clear? So overestimation is really easy to deal with. You just take a union bound. So the probability that we are to the left of bi minus 2 is the probability that something survives between sigma 1, the maximum, and 2 to the I minus 2, okay? And the probability that something in there survives is, by the union bound at most, 2 to the I minus 2, because there's that many elements times 2 to the minus I. That's 1/4, and I'm done. So overestimation is trivial. The whole name of the game is underestimation. How do I avoid underestimation? Okay? And observe that to avoid underestimation, what I'm looking for is that at least one element survives among the first 2 to the I plus 2. Right? That's what I wanted. So each element survives with probability 2 to the minus I. To avoid the underestimation, I need that at least one survives among those 2 I minus 2. So the expected number of things, like I showed you, that survive is 4. But now, when you look at this more carefully, the situation is like we have 2 exponential sized sets. One of them is the prefix of the 2 to the I plus 2 largest elements. And the other one is the random set that we expect, which is going to have size roughly 2 to the n minus I. Okay? So for generic values of I, those are both exponential sets. They must intersect with probability at least 1/2, because otherwise we're in bad shape. This is the underestimation case. But their expected intersection size is 4. Okay, so I have these 2 exponentially large sets. They have to intersect frequently, and the expected intersection size has to be 4. This seems like an incredibly delicate situation to engineer. Is this point clear? Right, so there is this set that I know nothing about. I know nothing about the geometry of this set. It is a subset of the cube. The only thing I know is its size. And I'm supposed to take a random set that will hit it so that the expected intersection size is 4, and it will hit it often. Okay? And of course, what I'm really concerned about is the possibility that, yes, I can have an intersection size in expectation, whatever it is that I like, but I'm really very much concerned about variance. Because if I want it to be the case that this probability is bigger than 1/2, the variance of the intersection has to be very small. So,
and so if we're perfectly uniform, then this should be trivial.
That's right. So for example, if I could ask each element of the domain to go away with probability p, life would be brilliant. Right? The problem is I have no way of encoding this, because ultimately I need to be able to optimize over this set.
So what exactly is it? I'm sorry. Does pairwise independence?
Yes. That's right. So we'd like to define a random set such that the probability that every element is inside is 2 to the minus I. So for example, we could take a random subcube. That would do the trick. It has to be efficiently describable, because ultimately we want to optimize over it. A cube would be perfect for this. But we want the variance of the intersection to be minimized. And now for this, you see that a cube is horrible. Because if, for example, my original set was a cube, and my random set is a cube, then what happens is these two will either have intersection of size 0, or will have huge intersection. So if the expected intersection is going to have size 4, this will only be the case because the probability that they ever intersect is extremely small. So it turns out that if you want to minimize the variance of this, it is essentially equivalent to saying I'm going to sum, there's this unknown set, like I said, set S. I would like to minimize this quantity, which is the sum over distinct elements of the set of the probability that sigma prime, different from sigma, is in the random set, given that sigma is in the random set. So I tell you that my random set does contain an element, R. Sorry, I tell you that my random set R does contain an element of S. What does this do for the probability of any other element in your set? We would like this to be small. And given that we know absolutely nothing about the geometry of the fixed set S that we're trying to hit, a very reasonable goal is to go for this, which is pairwise independence. Okay? So we'd like it to be the case that the probability that sigma prime belongs in our random set, given that sigma belongs in the random set, is essentially, not essentially, is exactly equal to the a priori probability. And observe that this must be true, like let's say if this is sigma prime at Hamming distance 1, this is sigma prime at Hamming distance n over 2, they should be equally likely to be in the set, given that sigma is in the set. Okay? And remember that we want our random set R to be relatively simple to describe. So we have some function, the characteristic function of the set, that tells us this is in, this is out. This function has to be simple to describe on one hand, yet at the same time it should have the property that if I tell you that this is in, it should convey the same amount of information for an element that is right next to it versus an element that is very far away. Which is sort of like a nasty function, right? The function that defines R has to be nasty if it decorrelates from itself so rapidly. At Hamming distance 1, you have no additional information, given that this was in. Turns out that some very smart guy solved this problem for us. And he solved it in a different context. So I'll just give a quick overview. The idea is to communicate over a noisy channel. We have some random variable, takes 2 to the k possible values. Alice is going to observe the random variable. She wants to transmit its value to Bob over a noisy channel. And for simplicity, we'll think that we're working over the binary symmetric channel, which takes every bit that you put in and flips it with probability p. And the solution that was suggested by Shannon was to say, listen, take a bigger cube, one of dimension n, where n is much bigger than k. Remember, there's 2 to the k possible values. And inside that cube, take a subset of size 2 to the k, and label each of its elements with one of the possible values of x. So when Alice wants to send a value to Bob, she sends the corresponding n-bit string in this subset that they have chosen inside the big cube. Bob receives whatever the channel does to this string, and then Bob says, well, I will find the element of the code that is nearest to this, and that's what I will assume was transmitted. And under very reasonable assumptions, this is the best you can possibly do. So why is this relevant to us? Well, this property that I mentioned earlier, that you would like it to be the case that knowing that something is in the set confers no information on the other stuff, suggests that we would like the geometry of our set to look very much like a mist. We wouldn't like there to be clumps in our random set inside the cube. And error correcting codes, I think, are a very good abstraction for a mist. So it is natural to look here. And the idea is, in the case of error correction, that if you look at the elements of your code and then you look at the ball inside each of the code words, if those are disjoint, then you can have error-free communication. And moreover, Shannon showed that asymptotically, selecting R to be a random subset of the cube is about as good as it gets in terms of the redundancy that you're willing to put in. The downside is that if you try to achieve communication in this fashion, the code book doesn't have any structure. If it's a random set, you literally have to write down every word in the book. So the code book that they have to live with is exponentially big. And moreover, when decoding time comes, Bob has to go over every element of the book to figure out what's the Hamming distance and determine what is the nearest. So another contribution that Shannon made in his pioneering work was to at least get rid of the exponential description length part of the code by showing that linear codes achieve the same kind of performance. And the way that things work in a linear code, and this, by the way, is exactly the same kind of random set that we wish for ourselves, is we define the code, which in our case is going to be the random set that we want, to be the set of solutions to a system of linear equations modulo 2, where both the matrix and the constant vector are Bernoulli 1/2. So this is a matrix where every entry is 0 or 1 with probability 1/2, and this is a vector where every entry is 0 or 1 with probability 1/2. And the first thing to observe is that for any fixed element of the cube, independently of what this matrix is, this matrix can be completely deterministic, the probability that sigma solves the system is 1/2 to the I just by the randomness inside B, okay? Independently of the randomness inside A. So one nice property that this construction has for us, it readily achieves the density part that we want. Meaning that if we define our random set in exactly this way, then the probability that any particular sigma belongs in the set is exactly 2 to the minus I like we wanted, and we control I by just controlling the number of rows in the system. Now the other thing to notice is we were interested in this probability. The probability that A times sigma primes equals B is in the set, given that A times sigma is in the set, okay? And observe that if you condition on A times sigma being equal to B, then this is equal to this. Is this clear? Because it is saying, well, they have the same value. And this one is equal to B, so therefore this one is equal to B. Observe, though, that this is something we can condition on without really exposing A. In other words, this part depends only on B, so we can actually just analyze what is the probability of this happening completely independently of B.
Sort of right, but I mean, that right-hand side does depend on A. I mean, if A sigma equals B.
For any,
I mean,
this probability is 2 to the minus I.
Fix A, then.
That's right, for any fixed A.
Right, but still you need to know what A is.
My point is I can analyze this probability independently of B.
So when you write probability now, you're randomizing over both A and sigma, or for A and B, or just...
So for this one, that's my point. In order to determine whether this event happens or not, right? It's enough to determine this probability. Okay. That's my point. And this is what we will determine whether the, in other words, I can perform the A experiment first and then perform the B experiment. And it's a perfectly legitimate way to go about it. So if this is sigma minus sigma prime, so these are the ones in that vector, observe that the only part of A that matters is what happens in the corresponding column. The remaining columns are irrelevant. And moreover, if we actually determine all but one of these columns, we still have a situation in which now these are numbers determined by everything but this, and we want these to take values so that when we take one more addition, we get to 0. So the probability is again 1/2 to the I. Is this point clear? Again, I want to compute the probability, that a particular fixed vector, sigma minus sigma prime, is going to evaluate to 0. That probability only depends on the non-zero columns of my vector. Imagine that I don't generate all of A at once. First of all, it doesn't really matter what I do with the white part. And then for the black part, imagine that for some reason, I first generate only the orange columns. At that point, when I take the inner product, they give me a number, right? And then eventually, to that number, I'm going to add this number, and my hope that the sum is equal to 0. Well, whatever this number happens to be, the probability is 1/2 that this will take the right value. So I still get 1/2 to the I, which is the a priori probability. So random linear codes have exactly the properties that we want. They give us sets, which we can control the thinness of them perfectly by just adding equations, and have the additional property of achieving pairwise independence. And pairwise independence is good enough to be able to perform the statistics that we want. So the overall idea,
So just to be
yes,
clear, what you're discussing now is you're saying that if I have a vector, if you have a fixed, a random matrix, random A, random B,
okay,
right? And I present to you one vector that satisfies A sigma, and
That's right.
then the chance that
any other vector,
yeah, that pairwise, you just show
Exactly.
pairwise independent.
Exactly.
Right? And that you just need no distance from your code. You just need
that's right, I don't need any distance
any
properties.
distance.
That's right.
Yeah, okay.
All I'm
Just
saying is,
parity will work, right?
that's right, in the way that I set things up,
Yeah.
I said I wanted to perform this summation, I reduced this summation to some probabilistic means, then I said that it would suffice for me to have pairwise independence.
Yeah.
And then I say, look, there is this construction of random linear codes that has exactly the properties that I want.
Yeah. Even a single path.
And I could use, well, I have to use, remember I have to set I to every number between 0 and n.
Okay, okay.
Okay, so the size of the matrix will grow depending on how big or small a subset of omega I want.
Just saying you're asking very little from your code. Right? You're asking.
That's right.
You
That's right.
You want
That's
your
right.
code doesn't have.
He's also not fixing the code, he's choosing the code randomly. So it's
Right.
different than, like sometimes we say, you know, if you take a code with large dual distance, then it has scalars in it.
That's right. So I'm not going to need things like large distance, for example. For now, I'm taking the naive approach, and all I'm asking for is pairwise independence.
And what if you used a different error correcting code?
Yes. So,
That's the next thing. All right.
so everything I've said so far is not my work. Okay. So this is the paradigm that Hermans and others have developed, and the paradigm says, define your random set R sub I by taking whatever system you had or whatever function you had and imposing the additional constraint that you will put in I random parity constraints, each of which though has roughly n over 2 variables. So remember this matrix A that I said was Bernoulli 1/2. Okay? So it used to be, let's say you had a satisfiability formula and you wanted to count the number of satisfying assignments. And now I'm saying, you know what, I only want to count those satisfying assignments which have the additional property that they satisfy this system of linear equations. That's it. And each linear equation is going to have roughly n over 2 variables in it because there's n positions and in each one I put a variable probability 1/2. And having done this, the idea is that I'm going to estimate B sub I by maximizing f subject to these additional constraints, okay? And all this is fantastic, except it doesn't work, okay? It doesn't work in practice. So this is the theoretical idea that doesn't work in practice, and the reason it doesn't work in practice, I'll explain this in a second, but before I get into explaining this, at a high level, for most interesting scenario in the world, this comes to the factor graph representation of f. F is defined by microfunctions, okay? Each factor had 3, 5, 10 variables in it. And now you show up and you give me functions that have n over 2 variables in them. And what's even worse, you say, I have to satisfy those constraints. And what's even worse is whenever one of these constraints is violated, flipping any single one of the variables in it fixes it. So if you think of it from a search point of view, the branching factor now is n over 2 per constraint. So the solver just dies. Does this make sense? I had a function f, and I had a solver that was really capable of working with f and optimizing it over a certain domain. And now I tell the solver, I want you to do the same thing, except you have to satisfy each of these linear equations. And just think of one equation, okay? Whenever such an equation is violated, it has n over 2 variables. It's a parity equation. So if you flip any one such variable, you fix it.
I mean,
So from the solver's point of view, this is complete confusion.
another
Yes.
way of saying, I guess what you're saying is, if my solver was some local thing that was exploiting the local structure of the function to go uphill, now you're saying maximize the function over this random dust, right? And this random dust has is linear minimum distance, in fact. So
That's right.
the point is just a bunch of random points. Then basically any local procedure is completely useless because the solver, you just gave a function defined over a random dust, right?
Well, no, actually, as we will see, that's not the case. I am actually here talking about the syntactic interpretation of my constraints. I'm not yet complaining that the geometry is wrong. The geometry has to stay like a dust because otherwise nothing can work.
But the local solver, if any solver, I don't know how these solvers work, it depends on the problem. But I'm saying if a solver is doing like gradient descent or being greedy or...
So for now I'm talking about solvers which actually exploit the structure of F. And typically, okay, so we will see there's two variations on this.
Okay, because otherwise you're going to...
I understand, so like I said, there's two variations. For now, the complaint that I'm raising is that these constraints bind too many variables at the time, on one hand, and moreover, whenever they're violated, every way of changing them fixes them.
Right.
So the branching factor in any kind of search is just immense.
I see.
Okay? So the problem that is depicted here is a problem that just has 100 variables, and admittedly it's a particularly hard problem with 100 variables. You have an Ising grid, and you have set up the temperature and the coupling strengths so that it is undergoing a phase transition. And in that realm, what happens is you can add a few constraints. By the way, this is the true optimum. You can add a few constraints, and the system will work. But after you add more than something like 15 constraints of this long XOR type, everything completely crashes, and then you only just recover things in a reasonable shape when the number of constraints gets huge. Okay? So the solvers die, and they die at 100 variables. Okay?
In the sparse parity, then you have like log-n variables.
So this is where we came in. This is the picture that we were facing, and the question is, what can you do to address it? And we address it sort of in two distinct ways. The first one, which is really elementary, and this is completely Pei's idea, is to observe that since this is a linear code, you can actually invert the dust, and you can rewrite the random set R in terms of the generator matrix. And if you write it in terms of the generator matrix, instead of having to maximize F over the original domain subject to these constraints, you can simply say maximize F over a subcube, but now whenever you want to evaluate F, you just push through the generator matrix and it tells you what happens up there. So there's two benefits to this and one downside. The benefits is that even for moderate values of I, this is exponentially smaller than the original domain. And the second one is it's an unconstrained optimization. So now to this, you can throw any kind of probabilistic hill climbing or whatever it is that you want. Okay? What is the downside? The downside is that now I don't have explicit syntactic access to F. I don't see, let's say, a satisfiability formula anymore. There is a black box. I give it X and it returns a number. Right? But if, for example, your solver was dealing with F as a black box to begin with, then you're perfect, you have lost absolutely nothing, except that the size of the domain has shrunk dramatically and you don't have any constraints.
But if who's dealing with it as a black box, you can't tell to solve the maximum problem, can you?
Again, everything I'm saying is in practice, right? In some sense, I started the talk, I don't think you were even here, by saying I will assume that P is equal to NP and move from there, right? So this talk is really aimed at practitioners, and one refinement of the point that you're making, I think, is if it is a black box, what is truly impossible is to produce a certificate of optimality. Whereas in other cases, when it's not black box, you have actually a chance during runtime to even get a certificate. So this is one contribution, and this works incredibly well. In fact, it is what allowed us to determine the true optimum, and then just to verify it by other methods took thousands and thousands of more effort. So this is very elementary.
So I have an observation here, yes?
Yes.
The strange thing that will happen now is, basically you're just going over the dimension of the code, right? So
exactly.
This is 0 1 to the k, where k is the dimension of your code.
That's right.
And now you just have a linear space, so
So now I think of this is the big world in which F lives, and there is this smaller world, and I have this lens.
Yeah.
And I take every element of here and I push it through the lens and it paints the dust for me. So I confine my search in this space.
But the problem is now, if F, let's say, had a sparse factor graph approximation.
I lost that. That's
you
right.
lost that
That's right.
because it goes through the general.
Exactly.
Unless, I mean, another discussion here that would be interesting is, are there cases where there's a factor graph for the function and the G are married in a way that keeps the sparsity in interesting?
Perhaps. I haven't thought about that. I mean, short versions, I haven't thought about this, but this is an interesting observation. But the main thing I wanted to point out is there's two advantages. It's unconstrained, the domain is smaller, but it becomes black box. And there are certain domains in which having an explicit representation of F makes all the difference in the world. In other words, you can't do this trick. If you try to do this trick, you just die a horrible death. So for these domains, we would like to go back to the original trick of using linear equations so that we have additional constraints. And the natural thing to try to do is to try to sparsify the matrix A. Okay? So rather than having each entry be 0 or 1 with probability 1/2, you could try to say that every entry is 0 or 1 with probability P. And unfortunately, that doesn't work. Okay? And the reason it doesn't work is the variance completely blows up. But it turns out you can do something more intelligent and use a low density parity check code, which by virtue of being a code retains the mistiness property. So I'd like to say a little bit how the mistiness property arises in an LDPC. And in order to get a sparse matrix to be an LDPC, the main thing that you have to instill is to make sure that there is a lower bound on variable degree. So if things are random, but you make sure that every column has, let's say, at least 3 ones in it, we will see that you get very good code performance. So,
and you want distance? Goodness.
What I will demonstrate here is an argument for distance. It's not going to be an argument for pairwise independence. Okay. In the analysis, I'm not even going to use distance, and I'm not even going to show you the analysis.
Because the other benefit of LDPCs, the reason people went to LDPCs is efficient decoding.
I will get to that.
Oh, okay.
Yeah. So just to show you how having a lower bound on the number of ones as opposed to just taking an absolutely uniform thinning of the matrix makes a huge difference. Imagine that you have a solution, you have some sigma, and then you go ahead and you change 1 bit. By virtue of changing 1 bit, this is going to have now to change to have at least 3 violated equations. Okay? Why? Because every variable appears in at least 3 constraints. Now, if you try to fix this, perhaps by flipping 1 more bit down here, you're going to violate another 3 equations, and maybe you got lucky. This one and this one happen to be where other ones were. Now you introduced another one. And in this example, because I am dramatically cheating, you are super lucky, and after changing 3 variables, you have managed to pair up all the mistakes. But in an actual random matrix, that's not at all what happens. When you make a change, this creates violations, and each of these violations creates more violations, and this gives you an explosive branching process such that closing all the cycles, which is what is required to have back to a new code word, only happens at linear distance. So the point that was missing, people did try to use sparse matrices before. The point they were missing, though, is instilling a lower bound on the number of variables that, excuse me, in the number of equations per variable, so that you get this code-like performance. So the good news is, if you take the approach that I spent most of the time talking about and you replace the random linear codes with random LDPC codes, you get phenomenally good performance. And the reason is, if you look at the weight enumerator factor of the code, it looks almost like a random linear code. In other words, this is, if you condition, let's say, on any particular element being a code word, the probability of something else also being a code word as a function of the distance. In the case of a random linear code, that's a perfectly flat function, as you would like it to be. If you do uniform sparsification, you get this, and this is what causes the blow up in variance. This manifests as the chunkiness in space. If you do LDPC, this is dramatically depleted, and in fact, we even have some distance properties. So you get really, really good performance. Specifically, in every problem in which we know the ground truth, you get the same accuracy as using long equations, except you're 100 to 1,000 times faster. And there's many, many problems in which we don't really know the ground truth, but this thing keeps giving meaningful results, at least results that appear meaningful a posteriori when you use them in practice to several thousand variables. And what is particularly nice is that adding all those LDPC-like constraints doesn't seem to put a heavy burden on the optimization procedure, meaning the running time is comparable to how long it takes to optimize F in the entire domain. So it almost comes for free. It's almost as if you can do integration at the same time that you can do maximization. And then one last point that we're currently exploring is, if you look at low density parity check codes, after we had random linear codes, one of the great advantages that they offer is that they make decoding dramatically faster. In particular, if this is where you start off, this is the received element, decoding in LDPCs can be done relatively naively by a simple local algorithm that just tries to do some kind of gradient descent. And what makes LDPC codes good is that, sorry, I didn't say what this is, I apologize. So think of the 2 dimensions as the binary cube, 0, 1 to the n. And think of the 3rd dimension as saying how many of the inequalities of the equalities defining the code are violated. So when you receive something from the channel, you get something which is here, and then your decoder meanders around until it finds a 0. Okay? And the idea is that in modern LDPC codes, this is something that can be done relatively fast. And the reason that it's done relatively fast is because if you look at the energy function of such a code, it looks very much like an egg crate. So again, think of these 2 dimensions as 0, 1 to the n. Think of the 3rd dimension as telling you how many constraints are violated. Ignore the fact that for illustration purposes this is perfectly flat. Don't think of it as perfectly flat. Imagine that it continued to an actual point. Okay? So the very centers of these are the code words. And when you transmit something through a channel, the channel will distort it to something which will hopefully stay inside the radius of attraction. And in modern LDPC codes, these things are very, very nice and smooth, so that almost any form of gradient descent will get you down. One thing which is cheating in this picture is that it depicts the volume of the bad area as relatively vanishing, right? If somehow you end up with something here, you don't know where to go. Okay? So the truth of the matter is that in a modern error correcting code, even though you have asymptotic optimality, the overall area that is covered by this is still the majority of the cube. Okay, but you don't mind that. The way that this plays in our scenario is, imagine that I have my function f that is overlaid on top of this, and I want to optimize f, but specifically I want to find the optimum of f only at those points. Those are the only valid points, okay? So I can tell my solver, you know what, why don't you just try to, let's say, minimize f and completely ignore the constraints defining the code. Just keep track of how many of them are currently being satisfied. If the number of constraints that is being satisfied corresponds to some generic area inside the cube, don't do anything, don't bother. Okay? You're nowhere close. Just keep doing what you would have been doing anyhow. But if at some point you detect that the number of linear constraints defining the code follows just below the number that corresponds to a generic area, let's say that you feel that you're here, you tell the solver, you know what, why don't you just stop and let me just decode down. So at any given moment, you're either doing decoding or you're doing optimization. So this is what we're working on now, and it seems very promising, but I don't want to say much more about it yet. But again, this is the point where you take an insight from a different area, like what is the geometry for what a physicist would call the Hamiltonian for a modern error correcting code look like, and exploit that in the context of efficient computation. Thank you.
there any more questions for Dimitris?
So in this random sampling that we're doing, how do you guarantee that you're getting full coverage?
I'm not sure I understand the question.
So each time you're taking, when you're solving your optimization problem,
Yes.
right? So you're sampling your search space,
I'm taking a subset of the search space, that's right.
right?
This is by sort of...
Yes.
Mhm.
In that first place, I'm just looking at the dispersion factor. Are you guaranteeing that you're going to cover and not going to leave any large gaps in your search space? Or,
Yes, the short answer to your question is yes.
and how do you ensure that?
Because the sense in which there are no gaps that suffices for my purposes is that of pairwise independence, which is strictly achieved by linear error correcting codes, which are computationally problematic, but which are also achieved by LDPC codes, which are not computationally problematic. So it's a little bit like, if you look at the tiles up here, it looks like a random pattern, yes? The number of holes that you see. But the truth of the matter is all these patterns, all these tiles are the same. So I have a pseudo-random function that is a function that got specified with a relatively little amount of randomness, because I just specified the matrix A and the vector B. And this defines an exponentially large pattern in my search space, which is sufficiently uniform for all my statistics to go through. It is obviously not as random as if I said to every element of the domain of the function, you stay in with probability P, but it is random enough. Or random enough, I can sort of prove a theorem about what does it mean to say random enough. Yes?
You say the variable